Okay, greetings. I am going to be using um, this platform to post to this simulation link for the pressure experiment, virtual or simulated experiment. Okay, all right. So it is hydrostatic pressure in liquid. All right, this is the link that is on the form that is provided. All right, for persons other than those in my class who would like to know where to find it. It is here. All right, it's called the Walter Pendant. All right, and it's a whole range of experiments. So let's just see it here. It's a whole range of experiments that is very good. It is very useful. All right. The link is here. It's not too long. Walter hyphen Fedit dot de slash html 5 slash f p hen forward slash. All right. So let's get to it. Now, in this experiment, as outlined in the instructions given to you by me, you are to select any of these liquid. Water should not be included. Okay, so any of these liquids you can select and work with. Now, you'll have a table, and your table would have observation in the first column. The second column, you would see pressure. Third column, you will see the depth, right? You are asked to choose values between 0.5, 5, since 5 centimeter is the max. Basically, you're moving this, you're increasing the depth as you're seeing here. All right. So instead of just moving it and recording, all right, you can input directly into here whatever um, that you want, and you will see the hydrostatic pressure recorded down here, and this pressure right here, right, that is recorded, that's where you put in the pressure. Take the second column in your table. All right, your value should range from from here go right down to 5. They want a large range of values and input. All right, so it's basically simple. And then when you're finished, you're going to plot your graph. It is important that you plot your graph in a way that is conducive um, and accurate. All right. Without further delay, let me see if I can share with you. If I can share with you the example that I have done on my own. So I am going to share with you the experiment that I carried out on my own so as to ensure that you are well equipped to do this. So here I prove my equation, starting with pressure, right? And I go right down pressure in a liquid formula, or we want to say pressure in a fluid, since liquid and gas is a fluid. And this is the pressure equation or formula that governs pressure in a fluid. Now I choose this benzene, and my density was 0.88 gram per centimeter cube. This should be cube here. Let me just put that there. Centimeter cube should be there. All right. And you see I have my first column. These are the amount of trials. So I guarantee 10 trials. All right. I started from 0.5. The depth was 0.5 to 4.5 for me. You don't have to use. It's best you don't use these values. Choose values of your own. Okay, choose values of your own. Um, when I put this directly into the simulator, it recorded 0.43 hectopascal, which is times 10 to the positive 2 Pascal. All right, so I continue, I go 1.5, I go 2, I go 2.5, you understand, until I reach 4.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Okay, I had 9 values here. I miss a value. I miss number 4 right there. All right. So I would maybe have gone down to 10. It won't affect anything. Just an example. All right. In your tables, please ensure that in your individual tables you put in you ensure that you have the number 4 there. Okay. All right. So after I do that, I plot a graph P against D, pressure against H, or depth. All right. So on my y-axis, I add pressure. On my x-axis, I have depth. All right. Then I use my equation of a gradient of a line to find. So what I would have done, I would have drawn my big triangle, right? And my x1 would be here. My x2 will be here. My y1 would be here. This value here. This line here would be my y1. And up here would be my y2. All right. And then I would take my most accurate readings. So this value minus this value, put it in the numerator. This value minus this value, put it in the denominator. And since I run it using a computer simulator, I got 0.869. That was my gradient. And please note the unit. I wrote my unit, Pascal per meter. All right. Then I read for my equation of pressure. I notice that I want to find G because that's the second aim, finding G. So I know it's going to be P upon rho H equal G, which is what you're seeing here. All right, this would basically be P upon H rho or rho H equal G. Now there are some housekeeping that I needed to do. I needed to change my gram per centimeter cube to kilogram per meter cube. All right, I needed to change, so there, that was supposed to be meter cube. All right, so you'll be seeing some corrections here, and I will be sending these corrections to you guys. All right, so we have that right there. Let's correct this, a cube. All right, so what I did, I changed out my density. All right, I change out the density. And you see my density up here was in grams per meter cube. I change it out into kilograms meter cube. All right, I change it out into kilograms meter cube. And I got, when I worked it out, I got 0.088. Got my gram was this in kilograms. And I put it over there. And I put my 1 times 10 to the minus 2, which is a centimeter cube. And I made my conversion, which is 1 times 10 to the minus 2, which is a centimeter cube. And I got this value. All right. Now, this value is my density. So 1 upon rho. And if you notice, this was your gradient. This was my gradient. All right, because that's what I plotted up here. Pressure divided by depth. All right, so that came to the gradient of my graph was that. So what I'm supposed to do now, I'm supposed to multiply the gradient by 1 upon the density. All right, and see here, 1 upon the density, and I get 9.875 meter per second square, which is approximately 10 meters per second square, and it is in a very comfortable range since the theoretical value of acceleration due to gravity is 9.81 meter per second square. Okay, and basically that's it for this lab. If you have any question, please reach out to me so I can give you the best of advice. Okay, thank you very much for viewing this video. I will make it available to you as soon as possible. All right, all the best.